శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008 లో స్థాపించిన కళాశాలలో MBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో అటానమస్ కాబోతోంది.
2014లో ISO గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే A గ్రేడ్, 2016లో NAC A గ్రేడ్, ఇప్పుడు NBA సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ.
Hi students, good morning. Today we are going to study about the sinusoidal oscillators. So how these sinusoidal oscillators can be implemented by using our operational amplifier. We know that as an oscillator circuit is going to produce a sinusoidal waveform when it is going to satisfy the two conditions. So that is, as an oscillator, we know that for producing the oscillations, oscillator is nothing but a circuit without any input signal. It is going to produce an output waveform. So we are not giving any input to an oscillator, just we are giving a DC supply voltage. So this oscillator is also called as DC to AC converter, can also be called as DC to AC converter. So why? Because here it is taking the direct current as input and it is producing output. It is producing output sinusoidal waveform. So we can say that oscillator is a circuit which is going to convert DC to AC, and hence in this oscillator, so if you observe the block diagram of the oscillator, so here you can see the block diagram of an oscillator consisting of an amplifier and a feedback network. So these two are mainly important in an oscillator. Amplifier is going to increase the strength of the signal. That means it amplifies the signal and it improves the gain of the signal, and it also improves the strength of the signal, that is by improving the gain of the signal. So in this way it is going to amplify the signal, as well as a feedback. That means a part of output will be fed back to the input, such that this feedback is going to be fed to the amplifier, and then it will be amplified. So with this feedback it is going to produce the oscillations. So how it is going to produce the oscillations, now we are going to see in our next slide. So here the feedback networks take a part of output of an amplifier as an input. So that means we are giving feedback from output of an amplifier to the input, and the sinusoidal circuit, that is the oscillator circuit, sinusoidal oscillator circuit is going to satisfy the two conditions. The first condition is the loop gain, that is here you can see the loop gain AV beta, which must equal to loop gain. We have to consider mainly the loop gain. It must be 1. That means the loop gain must be unity, or it must be greater than unity. Unity is nothing but 1. So the loop gain must be greater than or equal to 1. Then only this is going to produce the sustained oscillations. So as we have discussed this concept in our stability of op amp in second chapter, so their op amp is going to produce the sustained oscillations when loop gain becomes greater than 1. So there we are going to keep the beta value less than 1 for eliminating the sustained oscillations produced by the operational amplifier. Here also, here we have to generate, our main aim is to generate the sinusoidal signal. So we have to keep the loop gain greater than 1 or equal to 1. So that depends upon, the loop gain depends upon AV, which is the gain of the amplifier, and beta, which is the transfer function of the feedback factor, feedback transfer function. Beta is nothing but the transfer function of feedback. So, and the next, this is the one of the condition the oscillator must satisfy, and the second condition is the total phase shift produced by the oscillator must be 0 degrees or it must be 360 degrees. So it must produce 0 degrees phase shift. That means there will be no phase shift of the input signal, and whatever there will be no phase shift, or it must be around 360 degrees phase shift. So these two conditions must be satisfied for producing a sinusoidal wave for an oscillator. So based upon these two conditions, so we are going to discuss about mainly the two types of oscillators. First one is RC phase shift oscillator, and the second one is a Wien bridge oscillator. So RC phase shift oscillator, so the op-amp based oscillator, this RC phase shift oscillator is an op-amp based oscillator in which we are going to use the RC networks, so R and C networks, to produce the sinusoidal signal, to produce the sinusoidal signal as its output. So by using this that is in the feedback network, we are using the elements that is R and C, that is resistor and capacitor. So using these resistors and capacitors in the feedback network, we are going to produce the sinusoidal waveform. And in this RC phase shift oscillator, the RC phase shift network consists of three cascaded RC sections. So from this video, you can uh, observe the that is how we are going to, how this RC phase shift oscillator is going to work, and how it is going to produce sustained oscillations, and what are the different conditions to be satisfied, and why we are what is the gain, as well as gain and gain
electronics. In the previous video of the oscillator, we understood the working principle of the oscillator, and based on the type of feedback, we had seen the different types of oscillators. Now, one such oscillator is the RC phase shift oscillator. So, in this oscillator, the RC circuit is used in the feedback path. Now, this RC phase shift oscillator generates the stable sine waves, and usually they are used in the low frequency generations, typically in the range of audio frequencies. So, in this RC phase shift oscillator, the amplifier provides a 180-degree of phase shift, and usually either transistor or the inverting op-amp is used for the amplification. Now, in the previous video, we had seen that to get the sustained oscillations, the loop gain of the oscillator should be equal to 1, and the phase shift that is introduced by the amplifier in the feedback circuit should be equal to 0 or 360 degree. So to get the sustained oscillations in this RC phase shift oscillator, this feedback path should also provide a 180 degree of phase shift, so that the overall phase shift that is introduced by this amplifier in the feedback circuit is equal to 0. And by tuning the gain of this amplifier and the feedback circuit, it is possible to achieve the loop gain that is equal to 1. So now let us understand in this RC phase shift oscillator how this feedback circuit provides the 180 degree of phase shift. And before we see that, first of all, let us quickly see the simple RC circuit. So this circuit over here is nothing but the high pass filter, and it is also known as the phase lead circuit, because in this circuit the output voltage used to lead the input voltage. So first of all, let us find out the transfer function of this RC circuit. So here this output by input can be given as R divided by R minus jXC, where X is nothing but 1 by omega C. So we can write this expression as R divided by R minus J divided by omega C. And by dividing the numerator and the denominator by the factor of R, we can write this expression as 1 divided by 1 minus J divided by omega CR. So if we find the phase shift, then the phase shift 5 can be given as 0 minus tan inverse of minus 1 by omega CR, that is equal to tan inverse of 1 by omega CR. And as we know, 1 by omega C is nothing but XC. So we can say that the phase shift 5 is equal to tan inverse of XC by R. So as you can see over here, in this circuit, the phase shift depends upon the value of R and the value of capacitance C. So for very small values of Xc, the phase shift of the circuit will be equal to 0. And whenever R is equal to 0, at that time, this term Xc by R will become infinite. So at that time, the phase shift that is provided by the circuit will be equal to 90 degree. So in this way, this RC circuit provides the phase shift between 0 to 90 degree. And theoretically, to get a 180 degree phase shift, we need to cascade the two such circuits. So each circuit theoretically should provide a 90 degree of phase shift. But like I said, to get a 90 degree of phase shift, the value of R used to be a very small, or theoretically it should be 0. But whenever R is 0, at that time, the gain that is provided by the circuit will be equal to 0. So practically it is not possible to achieve a 180 degree of phase shift just by using the two RC stages. So in practical case, instead of two RC stages, we require more stages. So using the three stages, it is possible to achieve the 180 degree of phase shift. So here, each stage will provide a 60 degree of phase shift, and the overall phase shift that is introduced by these three stages will be equal to 180 degree. But because of the loading effect of the other stages, the actual phase shift that is provided by each stage will be slightly different. But if you see the overall phase shift, then the overall phase shift will be equal to 180 degree. So in this way, by using the multiple stages, it is possible to achieve the 180 degree of phase shift. And in practical RC phase shift oscillator, usually more than three stages are used to get a stable phase shift. For example, if you use four stages, then each stage will provide approximately 45 degree of phase shift. So combining all the four stages, we can get a 180 degree of phase shift. So in this RC phase shift oscillator, like I said, the amplifier is used in the inverting configuration. So it provides a 180 degree of phase shift. And through this feedback circuit, or through these RC stages, remaining 180 degree of phase shift is introduced. So the overall phase shift that is introduced by the amplifier and the feedback circuit will be equal to 0. And by setting the gain of this amplifier and the feedback circuit, it is possible to achieve the loop gain of unity. So here is the RC phase shift oscillator circuit, which is designed using the op-amp, and the same circuit can be redrawn like this. So as you can see over here, this op-amp is configured in the inverting mode. So it used to provide the 180 degree of phase shift. Well, in the feedback circuit, these RC stages used to provide a 180 degree of phase shift. So in this way, the overall phase shift that is introduced will be equal to 360 degree or 0 degree. Now in this RC phase shift oscillator, the attenuation that is introduced by this feedback stage is equal to 1 by 29. So to get a unity loop gain, the gain that is provided by this op-amp should be equal to 29. Now this circuit will provide a unity gain only at one particular frequency, and at only one particular frequency only, the overall phase shift of the circuit will be equal to 0. And if three stages are used, then this frequency f can be given by the expression 1 by 2 pi RC times under root 6. So at this particular frequency only, the loop gain of the circuit will be equal to 1, as well as the overall phase shift of the circuit will be equal to 0 degree. And if more than 3 stages are used, then in general for n number of stages, this frequency f can be given by the expression 1 by 2 pi RC times under root 2n. So if 4 number of RC stages are used, in that case, this expression of f will be equal to 1 by 2 pi RC time under root 8. And for 3 stages, it will be equal to 1 by 2 pi RC times under root 6. Now some of you might be wondering that how we have got this expression of the frequency, as well as why the attenuation of this RC stage is equal to 1 by 29. So let us derive these two expressions very quickly. So here the same RC stages are drawn separately. Now here let us assume that V is the input to this RC stage and V out is the output of this RC circuit. Now in this RC circuit, just by using the mesh analysis method, we can find the relationship between output and input, or we can also use the nodal analysis method to get the relationship between output and input. So by using any of these two methods, we can find the relationship between output and input. And if you find it, then you will get that this V out by V in for this RC network will be equal to minus 1 by 29. So let us quickly derive this relationship between output and input. So here let us assume that the voltage at this node is V1, the voltage at this node is equal to V2, and I1, I2 and I3 are the currents which are flowing through these three capacitors. So here what we will do, we will find the value of this V2, V1, I2 and I1, and we will find these four expressions in terms of the output voltage, and using these four expressions we will find the relationship between output and input. So first of all, let us concentrate at this node V2. So at this node V2 we can write this voltage V2 is equal to this voltage VO plus the drop across this reactance XC, that is equal to I3 times minus JXC. Now if you look over here, this current I3 is flowing through this resistor R. That means this output voltage Vout is nothing but I3 times R, or we can say that this current I3 is equal to VO divided by R. And if you put the value of Xc as 1 by omega C, then we can write this expression of V2 as VO divided by j omega Cr plus VO. That means V2 is equal to VO times 1 plus 1 by j omega Cr. So in this way we got the expression of V2 in terms of the Vout. Now similarly let us find out the expression of I2 in terms of Vout. So if we apply the KCL at this node, then we can write I2 is equal to V2 by R plus this current I3. Now we already found the value of this V2, and we know that I3 is equal to VO by R. So we can write the expression of I2 as VO by R into 1 plus 1 by j omega Cr plus VO by R. And if we simplify it, then we can write VO by R multiplied by 2 plus 1 by j omega Cr. So in this way, we got the two expression of V2 and I2 in terms of the output voltage. Similarly, at this node V1, let us find out the expression of V1 and I1 in terms of the output voltage Vout. So at this node V1, we can write this voltage V1 as V2 plus I2 divided by j omega C. That is the drop across this reactance XC. Now we already know the value of this V2 and I2. So if you put the value of this V2 and I2, then we can write the expression of V1 as VO times 1 plus 1 by j omega Cr plus VO by R times 2 plus 1 by j omega Cr multiplied by 1 by j omega C. And if we solve this expression, then the value of this V1 will be equal to VO times 1 plus 3 by j omega Cr minus 1 by omega square C square R square. Similarly, by applying the KCL at this node V1, let us find out the expression of I1 in terms of this output voltage Vout. So applying KCL at this node, we can write current I1 will be equal to V1 by R plus this current I2. Now we already know the value of V1 and I2, so let us put the value of V1 and I2 in this expression, and we can write this current I1 as VO by R times 1 plus 3 by j omega Cr minus 1 by omega square C square into R square plus the value of I2 will be equal to VO by R times 2 plus 1 by j omega Cr. So if we simplify this expression, then the value of I1 will be equal to VO by R times 3 plus 4 by j omega Cr minus 1 by omega square C square into R square. So now so far we got four expressions of V2, I2, V1 and I1 in terms of the output voltage. Now the only expression that is remained is the relationship between input voltage and the output voltage. So now let us write down the expression of V1 in terms of this I1 and V1. So now we can write this input voltage V in as voltage V1 plus the drop across this capacitance XC, that is equal to I1 divided by j times omega c. And let us put the value of V1 and I1 in this expression. So the input voltage V in will be equal to V out plus 1 plus 3 by j omega CR minus 1 by omega square c square into r square. So here we have just put the value of V1. Now let us put the value of I1 in this expression. And as we know, I1 is V out by R times 1 by j omega c, that is this 1 by j omega c into 3 plus 4 by j omega cr minus 1 by omega square c square into r square. So if we simplify this expression, then we can write this input voltage V in as V out plus 1 plus 6 by j omega cr minus 5 by omega square c square into r square minus 1 by j omega cube c cube into r cube. So this is the relationship between input and output voltage. Now the output voltage will only have a real part. That means the imaginary part of this expression should be equal to 0. So by equating the imaginary part to the 0, we can write 6 by omega cr minus 1 by omega cube c cube into r cube, that is equal to 0. Or we can simplify this expression as omega square c square into r square will be equal to 1 by 6. That means omega will be equal to 1 by under root 6 times rc. And if we write this expression in terms of the frequency, then we can say that f will be equal to 1 by 2 pi rc times under root 6. So now let us find out the gain of the circuit at this particular frequency. Now once the imaginary part is 0, then the expression can be written as V in is equal to Vo times 1 minus 5 by omega square c square into r square. Now in this expression, let us put omega is equal to 1 by under root 6 times rc. So if you put the value of this omega, then this input voltage V in will be equal to Vo times 1 minus 5 by 1 by 6 times r square c square multiplied by r square into c square. So if we simplify it, then the input voltage V in will be equal to Vo times 1 minus 30. Or we can say that V out by V in is equal to minus 1 by 29. So in this way, we can say that this RC network used to provide attenuation of 1 by 29. And here the negative sign indicates that this RC network used to provide a 180 degree of phase shift. So in this way, here by tuning the value of R and C in the feedback network, it is possible to get oscillation at particular frequency. Now generally in this RC phase shift oscillators, the value of R is remained fixed and the only value of capacitor is changed to get the desired frequency of oscillation. So here in this RC phase shift oscillator, all the capacitors are gang together. So just by changing the one capacitor, it is possible to tune all the capacitors. And in this way, it is possible to tune the circuit at one particular frequency. So this is all about the RC phase shift oscillator.
So student, this is what we have seen in a RC phase shift oscillator. So here you have observed that how it is going to produce a sinusoidal waveform using three RC circuits, as well as theoretically you have observed the concept, and as well as practical whatever the you have observed the how it is going to generate a phase shift. And the phase shift provided by the RC network is nothing but 180 degrees. And the phase shift here we are going to use op amp in inverting mode. So the op amp is going to provide the phase shift of 180 degrees. So totally 180 plus 180, it will be 360 degrees. So the total phase shift will be 360 degrees. In such a way, it is going to provide the, it is going to produce the phase shift. That is, it is going to produce a sinusoidal wave using this RC network. RC network. So this is what you have observed from this video. So today we will end with this session. Thank you, students.